So with that, I'll I think actually, Tom, why don't you introduce yourself a little bit? You're probably much better than me, but doing that. But it's great to see you from Atlanta. Okay, it's and I will stop sharing now so you can take over this show, so to say.
Thanks, Tom. I'll kind of introduce my background in showing some of this information. Um, I'm Tom McDermott. I'm the Chief Technology Officer of the System Engineering Research Center, which is a U.S. research center primarily funded by the U.S. Department of Defense. And we do um, kind of research on system engineering methods, processes, and tools in general. We also have a second center, which is called the Acquisition Innovation Research Center. And so in the US Department of Defense, they use a system engineering method to do material acquisition. So we now sort of cover the whole range of acquisition topics from engineering up through program management and test, law, business, procurement, all those other kinds of things in our center. We're funded about $35 million a year. There's quite a lot of research going on, and we're a bit unusual for what we call university affiliate research centers in that we're a network of universities. So we right now have 26 universities that collaborate together on system engineering research. So that's that background. Um, my background, I'm a computer architect by trade. So that's where I grew up in computer and network architecture. Spent 18 years with Lockheed. I'll talk a little bit about that in this presentation. 17 of those 18 years were working on the F-22 fighter program, leading up to being the director for the F-22 avionics program at the end of that career. Then I went to Georgia Tech for 15 years, and 6 of those I ran the Georgia Tech Research Institute, helped develop the system engineering master's program at Georgia Tech. And then I finally arrived at the System Engineering Research Center about almost 6 years ago now. So I've been in this position as Chief Technology Officer, or what we call the SERC, ERIC, um, since about 6 years ago. It's a great place to work. I get to pretty much work on what I want to work on. The research is really interesting, and we're in a really dynamic era of system engineering with things like digital engineering and AI. So we seeing a lot of change happening fast, and it's kind of great to be right in the middle of it. So I'm going to talk about system engineering in the era of human machine teaming, and in the process talk about this roadmap for AI and SE that we developed in my organization, the SERC. And so we originally developed this roadmap in, I think it was 2019. And that roadmap has been kind of useful in collaborating around the community in the topics of system engineering for AI and AI for system engineering, what we call SE4AI and AI4SE. We've used that to run a series of workshops. So at the end, I'll show you an interesting presentation from our last SE4AI, AI4SE workshop. We've done that for 4 years. And hopefully I gave you a good overview of the landscape of AI and system engineering in this presentation, going through quite a number of topics. So I'm going to start with a little vignette. This vignette was presented at INCOSE 2019, IS 2019, when we first started looking at the impact of AI and machine learning on systems engineering. So here we go. All right. So it's 5 p.m. in San Francisco, and rush hour is well underway. Traffic is flowing nicely through the intersection of Mission and Geneva streets. The Department of Transportation's new intelligent traffic flow system has resulted in wondrous improvements to the busy intersections like this. XYZ Corporation's automation technology has been flawless to date. However, a sudden power glitch at the intersection changes all that. The power failure temporarily shuts down the signal lights at the intersection for just a minute or two. But when power returns, the traffic command center discovers that they no longer have control of the signals, which are just flashing yellow. They try resetting the system numerous times, but cannot regain control. They go ahead and dispatch police officers to direct traffic flow through the intersection, and they call XYZ Corporation help center, but XYZ can't figure out what the problem is either. So XYZ's engineering department is called in to solve the problem. So XYZ Corporation, who's a leader in AI technologies, has recently deployed a system across its engineering teams. It's called DAISY, Digital Artificial Intelligence for Systems Engineering. It's designed to help automate many of the mundane tasks of engineering. DAISY also integrates the system engineering function in the organization, helping all the engineers to be better systems and critical thinkers by keeping track of the holistic view of their intelligent traffic management products. So DAISY gets to work on the problem right away. Its intelligence algorithms run thousands of simulations trying to recreate the San Francisco glitch in its numerous digital twin simulations of traffic flow. By 6 p.m. San Francisco time, which is 9 a.m., I think, the next morning in Tokyo, XYZ's engineering headquarters, Daisy has determined she cannot recreate the problem. It's time for the human engineers to kick in. And so that's when we see this global automated engineering control hub that's managed by Daisy kick in. So we have teams in San Francisco, New York, London, and Tokyo, and they're all assigned to help work this problem. So at this point, it's 4 a.m. in San Francisco. Oops, sorry. At this point, it's time to set the human engineering teams to work on the problem. So Daisy immediately schedules a virtual meeting at a common time between local engineering in San Francisco, Tokyo, London, and New York. Recognizing the early hour, Daisy allows the London team sufficient time to wake and prepare for this meeting. So at 11 a.m. Tokyo time, the engineers virtually meet and converse with Daisy's voice interface. Daisy recognizes that some of the Tokyo team has poor English skills, so she provides automatic translation of English to Japanese. Daisy also checks her human resources database link to make sure the right diversity of skills and potential ideas are present on the call. The team begins conversing between themselves and with Daisy to troubleshoot the issue. By the end of the hour, the team is isolated where they think the problem is, and it's agreed that the New York team will go make some changes to the digital twin simulations of the signal management system. It's already quite late in New York. It's 12 a.m., but Daisy handles the prerequisite overtime approvals and flex work schedules for these engineers. So the team in New York is assigned to do the simulation change, and the team in San Francisco and London are put on call for further directions and released to go home. Tokyo continues to monitor New York's progress. The New York engineers then do the job. Within 2 hours, they have updated the simulation software and able to recreate the problem in the digital twin. They sign off on the new simulation software back to Daisy and are released to get some sleep. It's now 7:30 a.m. in London. Daisy calls in the London signal management team and displays her analysis of the software. By 8 a.m., the London engineers are converting with Daisy. Daisy then implements the code changes itself, and by 9 a.m., an automated system reviews the data and approves the software change. Daisy's not finished, although it's 9 a.m. London time, it's 5 p.m. Tokyo time. The Tokyo team has been monitoring the situation and now can sign off on the change. Over the next hour, the team reviews the changes, tests the software in their signal lab, and approves the change release for all of XYZ signal management systems across the world. At this point, it's 4 a.m. in San Francisco, and plenty of time to deploy the new software and test it overnight before the morning rush hour. Daisy first provides a description of the software changes, then training instructions back to San Francisco to install and test the fix. DAISY has successfully taken a software troubleshooting and update process that would take several days and reduced it to hours. The engineers involved do not worry about the AI taking their jobs. They know that problem solving is still a very human discipline, but they appreciate the time that DAISY saves for them, particularly when emergencies happen outside of normal hours. They also quickly learned how to trust DAISY support. So this is a interesting, what we call AI4SE vignette. It's utilizing fully automated data search and model building capabilities that machine learning offers. It's also using man-machine teaming cognitive engineering assistants that are AI-based with humans. And finally, it's using mission-level digital twin technology in order to simulate and recreate problems. And the question is, how long is it going to be before we get to these flows, and what will they look like? And the bigger question is, are we going to be able to trust this level of automation? So that's the vignette that sort of started this exploration that led to the roadmap. And oh, by the way, if you have questions as I'm going through this, just raise your hand up on Zoom and we can be as interactive as we want to be. So that was the impetus for this roadmap. And this roadmap that we developed, it effectively looked at the emergence of human-machine teaming as an exponential growth in the things that we do. So we've always had human-machine teaming. I asked people, have you ridden your autonomous elevator today? So that teaming has always been there, but that teaming has not been based on learning algorithms. So a little bit about my background. I graduated out of Georgia Tech in 1984. I went to work for Lockheed. In 1985, I started working on the F-22 program. The F-22 is an interesting aircraft. It has an interesting avionics system. Its primary mission is to be able to locate, track, identify, and engage threat fighter aircraft beyond visual range. And so it can do that with multiple aircraft. And so you can see kind of a view of what the pilot's display looks like. There's a pilot and there's a wingman. They're communicating over a data link called IFDL, and they're assigning identified threat aircraft to be shot at, if you want to call it that, across the two of them. Now, what the F-22 avionics system does for this pilot is it actually autonomously detects threat aircraft, tracks their location and movement, identifies the type, calculates an optimal engagement, and even tells the pilot when to shoot. The pilot must initiate the shot. All this happens beyond visual range. So how does the pilot trust the information from the avionics system to accurately tell them what they're shooting at when they cannot see it in their visual range? And so this whole idea of automation and trust has been, it's been around for a really long time, but in complex systems like an F-22, it's been around since around the year 2000 when the F-22 was first tested and then deployed. So, we're 25 years, so to speak, into the development. The F-22 doesn't use any machine learning, but it uses a lot of AI. It uses Bayesian reasoning. It uses rule-based systems. A number of different components are incorporate aspects of AI in the system. And so the question here in a man-machine teaming is, how do we develop this trust? And I show this because this is not anything new. We've been doing this for a while. This is why system engineering becomes very important to the development and advancement of artificial intelligence. There's two components of developing trust. One is the engineer trust. One is the trust that the underlying algorithms are correct and reliable. And so we do that by having design reviews and verification and validation and all the other system engineering process. The other is called, I call it contextual trust. This is the trust that the pilot develops or the operator develops in the use of the system. And that is only developed with training and real world use. And so even though this rapid expansion of machine learning is going on, we have issues with machine learning, both in engineer trust, issues of explainability, and we have issues in contextual trust because the stuff is being rolled out much faster than we've seen previously. I don't know if you started to see facial recognition algorithms in your airports today, but it was about 5 years ago when those were first rolled out, and then um, quickly quit being used because we found that they were quite biased in terms of how they recognized faces. Well, it's been 5, 6 years since then, and the those systems are about 99.996% accurate these days against faces of all colors and genders and races. And so it's taken um, 5 years or so to develop the contextual trust in those systems that allow them to be rolled out again. So not all of machine learning is applied to human machine teaming, but in the end, that's going to be kind of the outcomes that we have to manage. So this is not really a new concept. It's being used in new ways. So, there was this really interesting crash that a Tesla had. It was about a year and a half ago, where the driver had put the car into an automated self-driving mode that allowed it to do automated passing maneuvers of traffic on the highway. And so there's two ways in a Tesla. You can have it in semi-automated mode where you have to push your signals and it'll do a passing maneuver for you, or it can do it automatically. And in this particular crash, not the one in the picture, but the interesting one, um, the driver claimed Tesla's full self-driving software caused the crash, and there's been several like this. But this one was really interesting because the driver said the car shifted over into the left lane um, into an oncoming vehicle that the driver saw, and the car would not let the driver take control back. And so there was an incident, and this came up. Now, I don't know what the outcome of that was. Conceivably, the control algorithms in the Tesla won't let that happen because as soon as you put pressure on the steering wheel, it disables the automated maneuvers. But it's just kind of interesting in terms of what we call transfer of authority, which is a core component of human machine teaming. How is control transferred between human and machine? And in autonomy and in artificial intelligence, this transfer of control is an evolutionary thing. When algorithms are first released, there's more human supervisory control. As they become more reliable, then the human moves more to an executive control and lets these algorithms um, do most of the work. And so what we call this transfer of control is we call it distributed autonomy. The autonomy is distributed between humans and machines. Um, and transfer of authority remains the primary concern in these domains. And so I'll talk a little bit about that first to open it up for the view of our roadmap. So if you've not experienced this, you're experiencing this transfer of authority when you use the Waze app or most other traffic navigation apps. We're not experiencing a machine control. This is more information control, but it's the same concept. And if your Waze was hooked up to your autonomous driving cars, then it would make these decisions on its own. And so if you look at the typical navigational app, you set the route, you set the time you want to leave and the time you want to be there, and then it automates the plotting of the route and the information over time. And so you take an action and that action hands off an order to the machine, the Waze app in this particular case, to follow a certain route. And the interface is set up to allow the interpretation of information between the human and the machine to be consistent and clear. And so there's interesting human interface designs that have to happen. Now, if you know, Waze has the capability to detect traffic conditions up ahead and automatically reroute you, which it does by proposing new routes. And so when that happens, Waze actually passes control back to the human and asks it, do you want me to reroute? And at that point in time, the human can make a decision to reroute or not. And so what you see is there's a set of rules in the system that drive those behaviors, and there's a set of authorities that are defined. And this is where system engineering comes into play, because even though we have these cool machine learning algorithms that may be able to rapidly assess traffic ahead by listening to other drivers, and then find new routes by optimizing plotting, we still have to do that based on a set of rules that are programmed into the system and a set of authorities that are passed back and forth, which is effectively a control loop, right? It's back to engineering again. So engineering has to be in this loop. The interesting thing about machine learning is it can monitor and process all this other contextual information for us. This is the value of learning algorithms as they're being employed today. And as we get into these more hardware intensive applications, the idea of making use of all that other information, like what drivers are reporting, what the speed of flow is, and all these other kind of things up ahead is really interesting. But the other really interesting thing about it is it's all built around the human intent and the machine intent, if you want to call it that. So the human intent is still the same. The machine is aiding that intent. And it opens up the question, how do these AIs interpret intent? It interprets intent today via a handoff between the human and the machine. And so in system engineering, we want to design these systems not just to employ machine learning algorithms, but also to employ new types of rules, and new types of authorities that respond to changes in human and machine intent as we go forward. And so this is really interesting to me. It's really interesting to see how this will play out in terms of human and team machining, human team machine interaction. So if we look at this on a broad scale, hierarchical control of distributed autonomous human machines, we've been doing some research with the Navy on what we might call robot wars to understand how humans and machines together plan out a mission and respond to a mission. In these contexts, we have stochastic decision processes. They're not physical. We have control by both human agents and machine agents. So Waze is a fairly simple example of this. We're ideally leveraging the distinct capabilities of each. And so the challenge here is transferring control quickly, safely, and smoothly back and forth. And that's really the system engineering challenge that we have today. So this can be viewed as a hierarchical control model. And it can be modeled in model-based system engineering tools, things like that. So although AI and machine learning is having great value in the computer science domain, and these things are being rolled out, there's a need for system engineering in order to manage primarily these control functions, these hierarchical control functions in their use. If we don't manage them well, then we get crashes, or we get bias, or we get other things like this in the AI world. What this does for system engineering is a big convergence of the human behavioral views of a system and the operational views of the system. So system engineering generally views the human system engineering as a specialty discipline. The operators and their roles and their workflows are often reduced to stick figures in a use case diagram while we focus on the machine, while human system engineering people worry about the task design, and they've been very distinct and separate. System engineering generally views simulation as a supporting process to design and development, but in the future, we're going to have to develop the training simulations, the simulations of the system first, and we're seeing that happen, for instance, in self-driving cars, because we can't evaluate and test every stochastic process in the real world. It would take many, many, many years to get these systems out unless we were able to take advantage of the computing power and high fidelity simulation in order to do that. And so there's this convergence that has to happen between traditional system engineering, machine level views, the human system engineering, task level views, and the operational systems engineering, the operational process views that doesn't really exist very well today. So I put this call out for this type of convergence over time. Not everybody's listening yet, but anyway, we have to become much more broader as system engineers in how we look at design of systems in the future. And we got to learn to share models and data across different types of programs. So right now we're re-engaging heavily between the system engineering community and the modeling and simulation community, which at least in the US has been fairly separated in order to start bringing these views back together again.
Tom, just a quick question. The CPHS, is that cyber physical human systems or?
Yeah, so sorry, I had another slide that I didn't put in here, but what we call that is adaptive cyber physical human systems.
Okay.
So that's a term that was coined by Azad Madni.
Thanks.
Monitoring chat. So a lot of the research that I've been doing lately is what we call design for consumption. So we have to be very much more purposeful in how we design systems to consume information over time. And so we see this if you go on the web and you see this type of design for consumption used quite heavily, where you have what's known as progressive disclosure of information. So if you use Waze, one of the things you'll notice is when Waze says there's an accident up ahead, you can actually click on the person who's reporting that accident and get a text-based short discussion of what that accident is ahead. And so you have this high-level view, but then you can click on the accident button and you can get more detail. It happens in sports now, so this is an example of an Atlanta Braves game, but this kind of general progressive disclosure information is a really interesting concept that has to enter into systems engineering. So the idea of design for consumption becomes a core part of how we architect future systems and how we design them over time. So with that, I'm going to launch into and talk about this AI and autonomy roadmap that we developed. This kind of came out of Fuse. So this was sort of a joint effort between the SERC and INCOSE Fuse way back at the beginning of Fuse. With the question, how do we prepare the future system engineering process in a world where humans and machines co-adapt to evolve to complex missions in response to dynamic operating system conditions? And so that opened up a question for us, recognizing that we need a lot of research. We need a lot of system engineering research to be done to answer this question. And that led to the development of this AI and autonomy roadmap that the SERC had presented. And we're now at version 3 of this roadmap. So it's been evolving over time. Version 1 was published in an INCOSE Insight special issue on system engineering and AI. Version 2 was then published in a book that was called AI and System Engineering, that was done as an output of several AAAI, Association for the Advancement of AI, conferences on system engineering meets AI. And then the third version I'll talk about came out with the release of a National Academy study on human machine teaming. So here's the current roadmap. It has 5 threads associated with it. One of them is technology evolution. So we realize that AI machine learning technology will continue to evolve. And what we want to do is work on things like transparency and explainability and bias, and then beyond that, uncertainty, quantification, and security, in order to do adaptation and trust. And so one of our big areas right now is standards of trust and trustworthy AI, with whatever trust means. The next thread is automation and human machine teaming. And that starts with how do we architect these systems? And so very few people are actually doing work in designing architectures of human machine teaming. That's an area that really interests me and that I've been doing work in. There's characteristics of those architectures like broad information flow with a narrow action that have to happen that are quite a bit different than what we've done in systems in the past. That leads us to situational awareness, which leads into trust again, then test and evaluation, and then adaptive simulation. Augmented engineering is what we call AI4SE. So there's a third thread that is related to digital engineering that says, now that we have digital representations of our systems, how can we automate or augment the system engineering process? That's the DAISY vignette over time. And so what we're seeing I'll show at the end of it one presentation, but what we're seeing in our SE4AI, AI4SE workshop is a great deal of presentations using large language models in order to improve the efficiency of the system engineering process. And I'll show you an example of that. So those things are what we might call cognitive assistance. Up here in the top corner, that's where we want to get at. But there's a whole lot of other things like automated model building and automated model checking that'll happen along the way. And all that is about how we use digital engineering. And then the last part of this is really workforce and culture. And so the SERC released the Digital Engineering Competency Framework a couple of years ago, which extended system engineering competencies out to data engineering, IT, and software construction and engineering. And so that is out there. We all have to become familiar with data and with how to maintain and use data. But the other part of this is really human and AI convergence. So human systems and system engineering convergence as we go forward. And so AI-enabled digital engineering is a key part of this. We can take advantage of all of the technologies that are going on, and we can use that with the right type of modeling in order to improve the way we engineer systems. So Tomokazu says, to design a human machine teaming system, I think we need a human model that works in the system engineering world. How would you tackle that? I'll cover that in a minute. So that's one of the things one of the areas of research. So we also need patterns over time that are part of what we do. We need information presentation views that represent the digital space. And then we need to take advantage of digital twins and incorporate AI in them. So all of these things are enabling us, digital engineering is enabling us to take advantage of AI over time. And so what we're seeing in this transformation is this convergence of data science and system engineering. And if you're not working the convergence of data science and system engineering now, you need to be focused on that. That's happening relatively quickly. And that's the core of, of what we're looking at in terms of system engineering transformation. Models become central to defining complex systems of systems. High fidelity simulation becomes the normal way to design systems. And this idea of we have to maintain two things in the future, the product and the virtual twin, digital twin of the product, becomes a different lifecycle set of processes for us. So it's all enabled by the digitalization of engineering. This study, Human AI Teaming State of the Art and Research Needs by the National Academies in the US, proposed a long-term research agenda in the human system side. We had proposed a long-term research agenda in the system engineering side. Those two things come together around this concept of AI system architecting. Long-term distributed and agile human AI teams through improved team assembly, goal alignment, communication coordination, social intelligence, and AI languages. And so that's where this convergence of system engineering and human system engineering or human system integration has to happen. And in our roadmap, this convergence shows up through a coordination of research. And so in the National Academy study, human AI team effectiveness metrics, and that gets to part of the question that was asked in the chat, but we'll cover that a little bit more, has to become part of the design of systems in the future. And then that's the core of what we want to do with architecting, which is human machine team design. There's a whole lot of things related to trust and uncertainty and false alarm rate certification that are really in the technology evolution space, leading us to AI flexibility, AI resilience, AI and lifecycle adaptation, and eventually AI as the team manager. And if we get to this point where AI is the team manager, effective teamwork and skills in AI, we need different types of mission simulation and training. So we call this pickup games, adaptive mission simulation and training. All these lead us to human machine co-learning over time. So there's a great synergy in this area. So what does this mean? Adaptive cyber-physical human systems, or modeling of cyber-physical systems as influenced by humans. Adaptive mission simulation is simulation and training that supports non-static objectives or pickup games. Most simulations are designed for stable outcomes, not to discover new outcomes. And so we have to evolve the simulation. And in the long term, AI resilience. And so a lot of our research, which I'm not going to go into here, is starting to look at how we can employ systems methods in order to look at AI systems or machine learning systems that self-adapt to changing operational boundaries, to changing environmental boundaries. So what happens is these systems are all fairly rigid and narrow and not adaptable, and so system engineering has to help in that domain. And so this concept of we need a human model that works in the system engineering world, how would you tackle that? It's very difficult to simulate human behavior. And so building a simulation of the human is quite complex. Because humans have to dream up the human outcomes, often difficult to do. And so what we really have been focused on are test beds. This adaptive CPHS virtual test bed was developed by Zamani out at University of Southern California, and it simulated a mission. And this mission The mission was a set of humans and a set of unmanned flying vehicles, quadcopters, to protect an asset on the ground. And so the question here was, how would we design this test bed or this simulation environment? So it had standard vehicles in it, but it had a smart dashboard that allowed the human and the machines to tailor their operations in different ways. And it allowed us to do research on the algorithms that allow those to be tailored in different ways. So you can change the control, you can change the level of human interaction, you could change the level of autonomous machine interaction. Had a scenario builder, so we have to be able to automate those different types of operational simulations by proposing scenarios and letting the tools do that. It had this hierarchical control model, and then it had a set of digital twins of the machine assets in this particular case. It allowed us to collect data and then trace the scenario execution in the test bed. And so the goal is to in this particular scenario is to optimize asset usage across a human and machine. The results are actually human machine co-learning. And so this is a fairly simple, software test bed. You can imagine this being incorporated into larger, operational test beds. And I don't know what it's like in Sweden, but I know in the US we're having some difficulty getting these large test beds set up to do this type of work. I know in China there's a large test bed that's a full mining operation that has autonomous mining trucks and humans working together. So they're exploring this much more robustly than we are in the US and perhaps a lot of the world right now. But this need for test beds becomes important. And then the second part of this is the need for models. And so there's a lot of research to go on in modeling human behavior. And this is the subject of the AAAI conference that's happening this year. There's a lot of it's modeling human behavior in conjunction with machines. So it's hugely complex, but what you really want to do is you want to model the human errors. There's a need to integrate the human and the cyber physical systems together to be able to run these simulations, and we need languages for that. We also need to be able to simulate the learning over time. And then there's a need to represent uncertainty into these decision models that come out of this. And so this is just an area of research right now. It's an area where a lot of people are doing research in order to produce product like driverless cars, but it's also an area where we need to understand the methodologies and the tools a lot better. So big focus area for our research. The evolution of AI and ML technology over time, we've talked a little about this, but the second area of research that we're heavily into is how to characterize the performance of these algorithms outside of their design boundaries. And what are the algorithms that let them self-adapt over time? And the idea here is to get to system level resilience, to get to behaviors that are more resilient, because machine learning produces fairly narrow response curves or performance in systems. So we're more watching this and experimenting with the evolution of AI ML technology because there's a whole lot of people doing this. We're more focused on these systems effects, the life cycle adaptation over time. And this is kind of an interesting way to look at it when we talk about uncertainty and error. So I'm an electronic warfare person. I'm an avionics person. I view characterization of errors as accuracy versus false alarms, hit rate versus false alarms, if you want to call that. And so we have this idea of characterizing errors as a hit rate versus a false alarm rate. And what you want to do is you want to maximize your hit rate and minimize your false alarm rate. This is a good way to look at how AI algorithms work. So if you fully maximize your hit rate and minimize your false alarm rate, you get a linear curve. But that's not necessarily very true in any type of complex systems. And so what you really want to do is you want to characterize this second curve here. What's the variance between hit rate and false alarm rate? And if it's equal variance, it's a nice curve. If it's unequal variance, then it's a more three-dimensional response curve over time. And the problem that we have with machine learning right now in these deep networks is we can't characterize that hit rate versus false alarm rate at all, except by many, many hours versus test. But on top of that, applying resilience strategies. So if they do make errors, they don't affect the not necessarily use of the system, but they don't harm anybody over time. And so we don't right now have any deterministic model to characterize variances versus false alarm. And this is leading us to this concept of trust in AI systems. And so trust is a little bit different in these systems because we have things like ethics um, and bias also dominating the conversation around with things like safety and other kind of stuff like that. So a lot of this research is how do we characterize the errors that these produce. In order to do this, we've got to take a test and evaluation. So we've got to view T&E as a continuum over time. So these characterizations are gonna vary and accumulate over time, and they'll happen throughout the whole life cycle. As we've seen with facial recognition systems, the performance has improved greatly over a period of 5 years, right? And so this evaluation time in the wild has to happen. We need test beds. We need test beds, and we've got a program that we're starting up right now, which is a AI algorithm characterization test bed that not just looks at the operational side of it, but looks at working backwards to the provenance of the data and how that drives the performance of these systems. It has to be relevant to the operational view because we have to evaluate things like resilience of these algorithms in use. And it's going to be probabilistic and risk-based. So it's going to have some kind of a probabilistic characterization of error associated with it. And we have to develop those over time. So the other big area of research for us in the SERC right now is test and evaluation of AI. We're both working on how we're going to do that in operational testing, but we're also working on things like these AI test beds where we can trace back into the development world and trace the provenance of these algorithms and how they're developed rigorously over time. And then the last part of this in the roadmap is workforce and culture. So digital engineering competencies, this is software construction, this is data analytics and data collection and anything else data. And this is the IT systems, the information technology systems that all this stuff is built on. These have to become part of every system engineer's competency set, right? This is the digital engineering competency framework because it's all going to be driven by data. Integrating AI ML experts with domain experts in all disciplines. So this is an area where we're seeing in real life a lot of concern. The AI and ML experts don't understand the context of the algorithms that they're developing, the context of use, and the domain experts don't understand how machine learning algorithms are developed. And these have to come together, or else we're going to have systems that are not safe or have high false alarm rates. We need evolving tools. We need tools that align design and disciplinary abstractions. So there's a lot of machine learning algorithm development tools out there. Most of them are open source and free, but we need tools to support that in the system engineering domain, which we might call higher order or more highly abstracted tools. Is there a question, Tom? Okay. Um, and then human systems engineering has to not be a specialty discipline anymore. So that's our roadmap. Last thing I wanted to do is give you an example of AI4SE from our SERC SE4AI workshop. And I stole these slides from a company, Celadon Solutions, who is in the process of putting a large language model based system engineering tool out on the street. And I found this to be one of the most interesting ones at this our last workshop that we did. So shamelessly stolen with permission for use here. But if you're not familiar with large language models, most people are playing around with these things today. They're AIs that generate output text from provided input text. Um, and that provided input text um, effectively looks at large vectors of language snippets across a huge corpus of text that comes in from all across the world. And so what they can do is they can answer questions, they can generate content, they can provide feedback, and they can be integrated in different ways with different domain specific tools. And so, if you haven't used Chat GPT yet to write a SysML 2.0 piece of code for you, it has now ingested the SysML 2.0 meta language, and it can do things like this for you out there. So it was software. Now we're starting to look at system engineering. There's a lot of them out there, and what's interesting is Chat GPT, that's probably the simplest, most constrained version. What you have to do is build what are known as layered models. And so the core layer is these very large, what's known as foundational models like GPT 3.5, GPT-4, and Llama and Bard. But you layer on top of that domain-specific models to tweak the language. And the real question here is how can these things help us do system engineering? Because system engineering is quite a bit of it is text-based, right? It ought to be perfect for large language models. So question, do you think the trust in LLMs can also be gained in the same way human-machine teaming AI can? So what you'll see here is that the use of large language models to do system engineering is a human-machine team, right? It takes skill to develop and use the large language model in a way that it produces useful results. And it takes some understanding of what those results should be to analyze what the results are and prevent what they call hallucinations or stray data from entering into the equation. So I think the trust is going to be also done in the same way. Now, the nice thing is as these tools come out, these tools will develop over time and will help us do that human machine team, if you want to call it, which they call prompt engineering these days. So it will help us do the correct type of prompting of these language models in order to get useful results out of it, because it's all in how you ask a question. That's the way they work today. You ask detailed questions, you get better answers out. You ask general questions, you get general answers back. And so, the interesting thing that they propose and what I see coming is what's known as declarative modeling. And so, we like graphical models in system engineering. We like block diagrams and things like that. Software people don't. Software people like declarative language. And so the current model methods are all based on graphical representations organized into views. In the future, it's all going to be based on declarative text or code, if you want to call that. And we'll build these models not by drawing them on whiteboards, but by making declarations of what we want the system to look like and querying these models for results on how to do that. And so these automated methods are all declaration based with dynamic query of information using the AI. And the tools you're going to see coming out, this is one example, are all about how do we query data in order to produce models. And so the goal here is speeding up model creation. Oh, I'm sorry. I thought I had an hour and a half, Tom.
Yeah, okay. No, it's just an hour, but
That's what I handle my
as
time.
those that need to leave, I mean, we will record this. If there are any questions, you put them in the chat, and we'll cover them before we hang up. I still can sort of be here, so yeah. But maybe we should not keep it too long. And that's
Yeah, so I'll whip through this because I've just got a couple slides left. So the idea here is we prompt the AI. The AI builds the model for us. It generates lists of requirements and block diagrams for us if we want to. And then we review that to accept the model representation from the AI. And this querying process allows us to um, effectively generate the feedback, define criteria, allow the AI to generate the models, and then build via feedback quality into the models. And so there's this sort of pass fail thing as we go through this process of developing, for instance, requirements where we can do a pass fail criteria on the quality of that requirement and then using language based or chat based feedback gradually improve the quality. So I won't go into the details of this. You can look at this presentation. It was done at the INCOSE / SERC AI4SE. The Celadon presentation was video recorded, and you can get it on the INCOSE AI Explorer website. But they have built now this chat interface as a set of prompts to build models. And I think we're going to see this happen rather quickly as things come back and come out, is that we're gonna go to these tools. And again, because something like a requirements generation is a language-based process, and if we can improve the quality and speed of that generation by using chat-based interfaces with effective prompting, then it's going to help us in the long term. We'll move away from templated-based requirements to things that are more developed dynamically. So that's an example of one of the tools that's popping up right now. And this tool is not out on the street yet, but it will be out on the street here shortly by this company, Celadon Systems.
And to be frank, I think a lot of the other tool vendors are really crunching now up some of these features. It's really happening.
Yeah, so you'll see these chat-based interfaces popping into most tools. I know Innoslate's working on one. It's not built out on their production system yet. I don't know what Cameo's doing, but I think this is something that's going to happen rather quickly, particularly for the upfront requirements generation, the block diagram generation, the test case generation, all these kind of things, which have traditionally been based on language-driven conceptualizations. That's going to happen pretty quick. So that's the end of my talk. A lot of stuff's been going on over the past 4 years in this area. One of the reasons why we don't have research papers at our workshop is because it's happening so fast. The technology is shifting way faster than us researchers can keep up.
So where do you, I mean, just a reflection now, if we now do what, create these systems, I mean, will there be an end to what the human input will be, or will we still sort of try to evolve these? I noticed in your presentation there's a lot of, if we now do this, we can get rid of some of the human, work, and then what eventually will be left.
So system engineering is fundamentally a problem-solving discipline. And AIs, we don't know how AIs will evolve yet to where they can actually solve problems. That may happen, but we don't know how it's going to happen. We don't have any predictions of how it might happen in the future. This general AI, as you want to call it. So at least for the meantime, you can think of AIs and machine learning being very useful to automate processes that we do, but they're not necessarily going to conceptualize problems and solve them. So
Right.
quite a bit of use for system engineers. In fact, more use for system engineers.
Yeah. Okay. Maybe we should take this one question here that we can cover before we end up from Tomakazu. I don't know if you want to put it on yourself, Tomakazu. You can unmute. Otherwise, I'll just read it out.
So I think the presenter already answered the question.
Okay. All right. Yeah. Thanks. But in that case, if there are no more questions, I'll like to thank Tom so much. I know I had some slides here, but I think in the interest of time, maybe we don't swap. I mentioned that this presentation will be available on the INCOSE.se website. I'll also put a link to it in the LinkedIn event. So I'll put a comment that if you sort of found out about this way, you will also get the link. So with that, well, it's an interesting future, a lot of things happening. So, and I think there's some good hints here from Tom of what we have necessarily need to step up to. So apparently we need to get much more into the data science, right?
Yeah, we do.
Yeah. All right. Thank you so much, Tom, as I said, and all participants. Great to have this turn up. And then we'll take it from there. Next seminar will be in March, and will be noticed at probably on actually how we make complex systems safer. So it has sort of a very good link to what we talked about today. So with that, thank you.